Hey there. Ever wondered how quantum computers stay reliable when even the tiniest errors can derail complex calculations? Today, we're exploring a groundbreaking study that's pushing the boundaries of quantum computing, using a surprising ally, reinforcement learning. Let's start with the basics. Quantum computers harness the power of qubits, which can exist in multiple states at once, enabling exponential speedups for certain problems. But here's the catch: qubits are incredibly fragile. A single bit flip, like a qubit mistakenly switching from 0 to 1, can corrupt an entire computation. That's where quantum error correction, QEC, comes in. Think of QEC as a digital immune system. It detects and corrects errors in real time, preventing catastrophic failures. Traditionally, QEC relies on decoders, algorithms that interpret error signals called syndromes to pinpoint where mistakes occurred. These decoders often use simplified models of noise, assuming errors are independent and random. But real-world quantum devices are far messier. Noise isn't uniform. It's correlated, dynamic, and influenced by factors like temperature fluctuations or crosstalk between qubits. That's where graph neural networks, GNNs, shine. These AI models excel at analyzing complex, interconnected data. By learning from experimental data, GNNs can identify error patterns without needing perfect theoretical models, a game-changer for real-world quantum systems. But here's the twist: even advanced AI can have blind spots. What if an adversary manipulated the data just enough to fool the decoder? That's where this research gets wild. The team trained a reinforcement learning, RL, agent, essentially an AI adversary, to find the minimal changes to syndrome data that could trick the GNN decoder. It's like a digital game of chess, where the agent learns to exploit weaknesses in the decoder's logic. How did they do it? The RL agent played a high-stakes game. It analyzed the decoder's predictions and targeted syndrome bits, the clues the decoder uses to locate errors. By flipping just 1 or 2 bits, the agent could cause the decoder to fail. And the results? It succeeded 91% of the time, with an average of just 1 bit flip. That's a sobering reminder. Even sophisticated AI isn't immune to clever attacks. But here's the breakthrough. The team didn't stop at exposing vulnerabilities. They used those adversarial examples to retrain the decoder, teaching it to recognize and ignore these sneaky attacks. It's like training a security system to detect new types of intrusions. The decoder becomes more robust, not just by fixing known issues, but by anticipating future threats. The implications are massive. This approach isn't just about improving one component, it's about building a self-improving system. As quantum computers scale, with more qubits and more complex architectures, traditional error correction methods will struggle. But by combining GNNs with adversarial training, researchers are creating decoders that adapt to unpredictable real-world noise. So what's next? The team plans to refine this adversarial training loop, making decoders even more resilient. And who knows? Maybe one day, these AI-powered error correctors will be the unsung heroes keeping quantum computers stable, enabling breakthroughs in cryptography, material science, and beyond. Thanks for watching. If you're curious about the math behind GNNs or want to dive deeper into how RL agents are trained, hit that subscribe button. Stay curious, and let's keep pushing the limits of what's possible.